Hi, thank you for attending our talk. I wish we were able to see you in person and hope that in the next year the things will get back to normal. As you can see from the title, the topic is very important because the internet, the biggest storage of all your funny pictures and memes, runs on electricity. And we are here to talk about internals of power generation automations, about vulnerabilities that we were able to find, and about what you can do about that. We are security consultants who have been working with different industrial solutions for many years. Actually, we have been doing it for so long that we have a long list of contact information of different system integrators and industrial vendors. So when an asset owner, for instance, a power plant, comes to us and asks for a service, we don't just give them information about vulnerabilities that we found. We closely work with all involved entities, including the vendor, to find together safe and reliable fixes and workarounds. We work at Kaspersky, and this research is a result of a teamwork, not just of the three of us, but also of Gleb Gritsai, Sergey Andreev, and Sergey Sidorov. Everything that we are going to discuss today was reported to the respective vendor. I'm talking about Siemens a long time ago, but actually this is not one vendor problem. You can find similar issues in systems of other vendors as well. We are going to talk about real vulnerabilities in real power plants out there, and at the first glance, it may seem irresponsible. But if you think about it, for good guys to do such research, it's a challenge. You would need to have relevant experience. You will need to have a lot of time, and of course, you will need access to the industrial environment. So there is no walk-ins welcome sign on power plants doors, right? So for good guys, for penetration testers, for auditors, for power plant operators, it's challenging to get access to all of the things together. On the other hand, for bad guys, for those bad guys who would be willing and able to attack a power plant, um, it's their daily job to do such research. They have significant investments, they have a lot of time, but they keep their vulnerabilities to themselves for their malicious purposes. So we assume that those guys already have all this information, and from our side, we would like to share this information with good guys, with you, so you would be able to act upon this. Power plants is the main source of electricity on our planet, and thanks to carbon monitoring, anyone with internet access can get information about where different power plants located on the world map, what fuel they use, and which is their capacity. The heart of every power plant is a turbine. We don't have a picture of a turbine here, but if you ever saw a modern airplane, I believe you also saw a turbine. This is a giant rotating thing generating electricity. And on power plants, they look and work quite similarly. And turbine manufacturers are generous enough to share information where the turbines are used. Here, for example, a screenshot from Siemens website. Um, Turbines are used not only on power plants, they're used in many different areas like chemical or oil and gas and many others. But if you correlate this picture with the previous one, you will be able to understand a solution from which vendor is used on a particular power plant. In addition to that, online you can find a lot of information about what solutions are used in certain power plants, in different press releases, marketing materials. You can find a lot of interesting information about software, hardware version, generations of different systems. Sometimes you can even find building plans. Here, just a small example. Okay, Google, show me some power plants of California. Here are just a few power plants of California, and they have one more thing in common. They use the same plant control system, SPPA-T3000 from Siemens. This is exactly the system that we are going to discuss today. But before we move on to power plant generation, automation, let's talk a little bit about power generation process in general, what we are going to automate. Um, Here and throughout the presentation, we will be intentionally oversimplifying a lot of things, partially to make them more suitable for the audience, and partially because, to be honest, we don't fully understand them ourselves. So let's go from right to left. At first, you will need some fuel. Here is coal, for example. You put fuel into a combustion chamber, put it on fire, and it generates pressure to rotate a turbine. The turbine is connected to an electricity generator through a shaft. So when it's rotating, the generator starts generating the electricity. But it's important to mention that electricity doesn't go straight to your house or a city. At first, it goes to a special place called power grid. Uh, Power grid knows information about market demands. It receives energy from different power plants. And this is power grid who distributes electricity to consumers. During the burning process in the combustion chamber, you can have a lot of excessive heat, so-called waste heat. And there are different ways how to approach it. You can release it to the air through a condensing tower, or you can reuse it, do recuperation. For example, warm water and send the steam to a turbine to generate more electricity. Systems that are used to automate this process are called distributed control systems, or DCS. They are designed to make life of power plant operators much easier. They allow you to conveniently start and stop the power generation process. They allow to control the amount of electricity you want to generate. You just enter there the amount in megawatts that you want to have in the output. And they allow you to monitor everything. These systems are literally very powerful. They are connected through PLCs. They're connected to many parts of the plant, including the turbine, and they control such interesting things as the amount of fuel, the temperature of the combustion chamber, the rotation speed of the turbine, and even control the turbine not to go into different dangerous modes. Obviously, it's not a small piece of software that you just install on a server and it magically works. It's a very sophisticated system consisting of different hardware, software, PLCs, input-output modules, the turbine itself, and a lot of things. And often starting to create such a system starts even from building construction. So someone comes to a vendor and says, we have an empty field, please build us a power plant. And there are many vendors who do this, but today we will be talking about Siemens. The DCS from Siemens that we analyzed is called SPPA-T3000. Just like other DCSs, it consists of many different industrial components, PLCs, OPC, different servers, HMI, a lot of things. And it may have very different architecture depending on the site. But there will be two components that are unique for SPPA-T3000. They are called application server and automation server. And this is how we will structure our talk. First, we will talk about application server, then we will move on to automation server, and then we will move on to conclusions. In different manuals and documentation from Siemens, you will see how the system should be built in a perfect world. For example, they will say that the application network where application server is located should never be connected to any external networks, and how everything should be designed. However, also we again here very oversimplifying everything. In reality, in real power plants, you will need a lot of interconnections to other systems. For example, you will need a sensor network to monitor different vibrations inside the turbine. You will need demilitarized zone because you will need to get some kind of remote support from the vendor. You will need to get updates for your operating systems, for antivirus, and so on. You will need to push out OPC traffic to your corporate network or to a regulator because this area is very strictly regulated. So on practice, you will need a lot of interconnections. The life of our vulnerabilities started almost 2 years ago. Back in November 2018, we reported a bunch of vulnerabilities to Siemens. And about a year later, Siemens published an advisory containing information about how to approach these vulnerabilities and also a set of other vulnerabilities that were reported by other vendors. Other teams, and that's great that this area receives a lot of attention from security researchers. But also about a year passed, it doesn't mean that during this year Siemens didn't do anything. The thing is, SPPA-T3000 is an exclusively supported system. It means that a system integrator for this is Siemens themselves. So soon after we reported these vulnerabilities, Siemens started to roll out patches and working directly with their clients to fix everything. So December is just when this information became public. We don't have a lot of time to discuss in detail what kind of attacker, what can do with the system. I will just highlight that CVSS scores given here obviously do not represent how critical these vulnerabilities for real power generation process. They're just individual scores for vulnerabilities in the vacuum. To better understand what kind of attacker can do what, you can take a look at our threat model that is published in our white paper. Let's start with application server. Application server is a logical core of the entire system. Everything has connections to application servers in the logical sense. If anything needs to connect to the network, it will end up in application server. Other servers start their work from downloading software from application server and launching it. So this is the heart of the system. And what can possibly go wrong if you open over 40 ports there? This is, for an attacker, this is a huge attack surface. If they are lucky to get into their respective network, they can choose what they want to attack. Do they want to attack Windows operating system because this is simply a Windows server? Do they want to attack third-party components? Or they want to attack own SPPA-T3000 services which are based on Java? Also, we hope that these vulnerabilities are already fixed. In industrial environment, usually you don't update your systems very often. Usually it's about a half of a year or several months between major updates of operating system. So it's always possible to find a time window with remotely exploitable vulnerabilities in Windows operating system. Configurations also could be better. You can find some statistics for security benchmarks on the right-hand side. But one of the biggest problems is actually passwords. The life of passwords has 3 stages. At first, passwords were the same for all power plants. They were default and the same everywhere, and you can find them online. Obviously, this screenshot were not from information published from Siemens. Some power plant separators decided that it would be a good idea to share passwords and a lot of other technical information with the internet. But they're available online, and we also have a word list in our white paper. Around 2014, 2015, Siemens started to generate different passwords for different locations. However, the process of changing them was challenging. You would have to be familiar with the process to change the passwords by yourself. And only in the last year, in 2019, the process became easier, and now you can do it yourself much easier. Now, please welcome Radu, who will tell you about vulnerabilities in Java.
Hello, everyone. Let's look how SPPA software works on application server side. Operator can communicate with system through thin or fat client. In case of thin client, it uses Java plate of Internet Explorer and communicates with server over HTTPS. So it can be outside of application network, and its communication can be constrained by firewall. In opposite, in case of fat client, operator should belong to application network, and fat client directly communicates with RMI registry to found RMI services, and after that directly communicates with these services. Illustration of SPPA architecture was kindly provided by system through public URL. So not to be messed, let's divide it into spaces. In red zone, there are items that process HTTPS requests, and in green zone, there are RMI services. RMI service looks like network services which are served on dynamic TCP ports. SPPA consists of containers. All types of containers are represented on these illustrations, and containers has self-explanatory names. So before we go deep inside internals of SPPA, let me introduce some tools which used in this research. First of all JARS files of SPPA are obfuscated with commercial product, but this security measure can simply be bypassed by public available tool. Secondly, sometimes it is useful to see how legit software communicates with server. It helps to understand architecture and to see client workflow. In case of SPPA, RMI dissector was written. It represents raw TCP streams and in human readable format. Inside, it used read object method of SDK. It is known that this method is suffer from insector deserialization vulnerability, so be sure not to be exploited through remote pickup. The first pillar of SPPA is Apache Web Server. According to its configuration, folder Orion software config can be accessed by an unauthorized user, but in fact, this folder contains some critical information about application and about items of application and automation network. Also, configuration of Orion web application in Tomcat also can be accessed. Tomcat, there are 3 web applications registered in Tomcat. There are remote diagnostic service, manager, and Orion. According configurations of Apache and Tomcat, all these applications can be accessed by an authorized user, and inside Orion web application, there are servlets which can be accessed. All of them are listed in configuration web.xml, and the list is huge. Some of servlets has attractive names for attacker. For example, browse servlet. It allows an authorized user perform directory listing on arbitrary folder, but in case of exploitation, another servlet is more useful. File upload servlet allows an authorized user perform file upload and folder is fully controlled by parameters based dir and target name of HTTP request. This vulnerability can simply bypass to remote code execution. For example, attacker can corrupt some startup scripts of SPPA or simply inject JSP shell in Tomcat web application. and get remote code execution with system rights. Also, there are servlets, which has a service factory in its name. This servlets redirects HTTP requests to RMI services. Inside, it use parameter service URL of HTTP to identify RMI service, which will be called, and serialized object in a data section of HTTP request contains information about method and arguments which will be called. So there are situations when a thin client and fan client can communicate with RMI services, but in case of fat client, in case of fat client, it can communicate with RMI registry. So if application server miss some important security updates of Java, then server contains insecure deserialization vulnerability, and public available tool YSO serial can allow exploit it and perform remote code execution with system rights on server. So the next task will be to identify all input vectors for attacker, and for this task we will try to list all RMI services in system. At first step, we will use a class locate registry of SDK and get a big list of RMI services. All but one are GMX RMI services, and I assume that they used to control and manage containers of SPPA. For further investigation, we will choose lookup service. In fact, it looks like a collection of next level RMI services, and using its public methods, we can get the reference to this next level RMI services. The next level RMI service should implement interface service factory. So it also looks like some collections of another next level RMI services, and using public method get service and parameters such as client ID and name of the service, the instance of next level RMI service will be created, and reference to it will be returned to client. And this next level RMI service is a server which perform real job of SPPA, but in fact it contains a lot of public methods which can be accessed by an unauthorized user. So input vector of SPPA is very huge. The next question is to understand how authentication perform on a system. For this task, let's look how a client perform request to security service. To do this, first of all, client tried to get reference on security service with some client ID. In its turn, PC Service Factory use this client ID to get valid session in Session Manager. If Session Manager will fail, then exception will thrown and client request will be rejected. But in case of success, valid session ID will be returned to PC Service Factory, and in its turn, PC Service Factory create instance of security service where session ID will start in login ID, and a reference to this instance will be returned to client. Further, client can call some public methods of this service, and in its turn, these methods can perform some privileges checks of client. So we have two security measures of system. But there is a question: how client can perform login operation on system if he doesn't have any valid client ID? For this task, at startup of SPPA, session manager create anonymous session with client ID 0, and client used this client ID and perform login operation. But attacker can also use this and simply bypass this security measure. So to sum up, we have there are a lot of RMI services which has a lot of public methods, and permissions checks are fully delegated to this method. So it's really difficult to perform security management of this system. So we understand all input vectors and security measures. So it's time to find vulnerabilities. In the list of RMI services, there is AdminService. It can be accessed by an authorized user, and its public method transcript doesn't have any privileges checks. In fact, inside it, first step, create instance of class loader using bytes from arguments. In fact, this step will load arbitrary Java class. This class should implement interface admin script and define method execute. This method will be called by a run script of RMI services. For this case, we create Java class which simply run OS command, and this OS command will be run with system rights. In fact, there is more powerful post-exploitation because we inject arbitrary Java class in around SPPA software. So we can use some Java reflection and patch some private variables of SPPA, and as a result, we can corrupt some technological process of SPPA. To bypass privilege checks in methods, we can use second vulnerability. It's using RMI service session service and its public method get login sessions, attacker can get information about all login user on the system. This information contains usernames, IP, and client ID of login users. Attacker can reuse this, and if system if in this information there is a user with admin rights, then attacker can simply reuse his client ID and get the reference to security service with more privileged session. And after that, attacker can call public method get all users of security service, and as a result get all private information about all users on system. Moreover, password hashes also contains in this information. Both of these vulnerabilities can be accessed from either external or application network. All communications between RMI services are unencrypted, so username and password hashes are transferred in plain text. Moreover, system doesn't have any session protection mechanism. This fact is more critical in case of fat clients because of attacker can perform mid attack on the user of SPPA and get valid username and password hashes from the traffic of user, and after that simply reuse this username and password hashes and perform login operation on the system. Moreover, attacker can also change the password of the user. I talk a lot about password hashes and users, so it's time to understand how these items are organized on the system. So, Alex, you're welcome.
Hello, everyone. Let's continue our discussion about application server. On the previous slide, you could see how remote authentication works. Now I'm going to tell you about how it's organized locally. After the system gets started, it begins to read the content of files users1.xml and pdate1.xm to get user list and their password hashes. User1 is a simple XML, while pdate1 has a slightly more complex structure. It's a gzip archive encoded in base 64. There is a Java serialization object in the gzip archive containing a specific XML. The field of this XML from pdate1 file are presented on the slide. They are used to calculate password hashes and check it during user authentication. At the bottom of the slide, you can see password check algorithm in pseudocode. The cryptographic scheme is a typical crypt hashing scheme like in your Unix and Linux machines. It has solved different number of iterations, and the only one thing which was added is hard-coded solved. The same for all users, which is concatenated to the password. The tool to extract password hashes and their parameters from pdate1 file has been developed. Its output is presented on the slide. The tool can be used during password auditing to check weak or dictionary passwords and their hash calculation parameters. The tool is available in our GitHub repository. Draw the line under application server analysis. As you have seen, attack surface is really huge and include Java remote sources, Tomcat applications, and a lot of other. Secondly, it's about remote connections. Whether SPPA has or has not remote connections according to vendor, system integrator, or someone else, you should check it. And the good starting point for this is application server, because OPC maintains remote operator. All of this thing will end up on application server. Thirdly, despite the fact that there is automation network between application server and field devices, an attacker can affect generation process from application server. These actions include to start stop generation, change power output, or just get information how power plant works. Of course, such ventilation will always be visible for operator, always monitoring technological process. So real attacker will also be required to change or modify data on operators' HMIs, but it's also possible with revealed security issues. That's all about application server. Now let's move on to another main component of SPPA infrastructure, automation server. Automation server, the main goal of the automation server is to execute real-time automation functions and tasks for power plant control. Depending on power plant project architecture and features, the role of the automation server can be different. We have distinguished three roles, and the first one is automation. There may be slight confusion because the term automation is used both for server and its role, but analyzing automation server configuration and publicly available information about it, we have found that whatever the role is, almost the same hardware and part of software are used. So we have decided to use this kind of role classification, which seems less confusing to us, but at the same time, it's slightly different from the vendor's one. Anyway, having an automation role means that the server is responsible for interaction with input-output modules, which control and monitor power plant equipment such as turbines or electric generator. The second role is communication. This role is used to communicate with third-party systems. In other words, it's just a protocol converter supporting such protocols as Modbus, IEC 101, 104, and some others. And the last role is migration. In this role, SOA is used to connect previous version of SPPA, such as SPPA-T3000 or Perm-ME. In automation role, automation server can be run both on Siematic S7 PLCs or industrial PCs. In case of other roles, it can be run only on industrial PC. Let's talk a little more about each role, and let's start with automation role based on PLC. PLCs are what directly control field devices, and access to them is game over for any security discussion. Any configuration changes and updates for PLC required to stop technological process. Therefore, these devices usually have security misconfiguration and firmware without security updates. Another common security issue for PLCs is using unsecure industrial protocols. In case of SPPA, they are Siematic S7 protocol and PLC data protocol. There is quite a lot of information about S7, but not so much about PLC data protocol. So we had to deal with it and analyze it ourselves. It's not a special protocol for SPPA. When you program your PLCs and you need to exchange some data between them in real time, you use this protocol. It's pretty simple, and maybe its description is available somewhere in the internet, but we couldn't find it, so just in case, show its structure here. It doesn't have any security mechanism, and the only obstacle while do man-in-the-middle attack to spoof data is a sequence number, which we can get from a packet and just fuzzy incrementation. For protocol analysis, the Wireshark dissector has been developed and also available in our repository. During PLC security assessment, one of the main things which we check is unauthorized access to reading and writing the PLC memory. Availability of unauthorized access is determined by the position of mode selector of Siematic PLCs and some other configuration parameters. The matrix on the slide shows unsecure states for Siematic PLCs when unauthorized access is possible. The tool for gathering information from PLCs over the network and for its analysis has been developed by one of our colleagues and also available in our repository. Now let's talk about automation server based on industrial PC. The workflow of all roles in this case is quite similar to each other. When automation server is based on industrial PC, it's just a Linux box. During the start, it tries to download some additional files from application server. These files include jars, which represent runtime SPPA runtime containers, bar script, some configuration, protocol configuration files, and other. In order to execute downloaded jars, PTC Perk virtual machine is used. It's a real-time Java virtual machine widely spread in industrial and military areas. After that, running jars open RMI services or some of the extension. In case of migration server, Orion RPC services, which are extension of classic Java RMI services, are used, and you can see the listing on the slide. Automation server based on industrial PC has following security issues. Firstly, there is a possibility to spoof downloaded from application server files. These files are downloaded over HTTP, and there are no security mechanism like authentication or integrity check during this process. Secondly, it's about using default credentials, user CM admin with password CM. Thirdly, it's RMI services running on automation server. The research has found two vulnerabilities in Orion RPC services. which allow to perform sensitive data exposure and RCE. And the last group is vulnerabilities found in the software used to fulfill a migration role for connection previous version of SPPA. SPPA-T3000, also known as TXP. All these vulnerabilities found in migration server software are related to different kinds of overflow, stack, heap, integer, and other. Actually, there are so many overflows here that this talk would be overflown by that if we started to describe all these vulnerabilities in details. A few words about RPC vulnerabilities. These vulnerabilities have been found in runtime engineering service. This service has a method, a request runtime container where the first argument defines an action to be executed. Using the action read file, it's possible to read any file from the system. Using write config file action, it's possible to write any file to any folder in the system. And for example, it can be jar file, which executes shell command from the command line. And then using the same request runtime container method, it's possible to execute this, this jar later. That's all about automation server. To sum up, automation server can be run on PLC or industrial PC. In case of PLC, it's a usual PLC with well-known security issues. In case of industrial PC, it's a Linux box which tries to download jars from application server and then execute them with PTC Perk virtual machine. An attacker can spoof downloaded files or just exploit revealed vulnerabilities in network services. So far, we haven't mentioned any network equipment used in distributed control systems. During the research, we saw a wide variety of network devices and network infrastructure. They include different kinds of switches, routers, firewalls, and more rare devices such as data diode, for example. We tried to summarize all this information and got common SPPA network topology scheme presented on the slide. We have shown in purple usual places for network devices, but it also should be mentioned that the same devices in the same places can be found in other distributed control systems from other vendors. Network devices in industrial network usually have a lot of security issues. The reason is these devices don't require any configuration and can be run out of the box. Therefore, the things like weak community strings in SNMP, weak credentials in HTTP, FTP, Telnet, and other services, firmware with publicly available exploits, and just security misconfiguration, all these things is common and typical for industrial network devices. Additionally, some industrial protocols, for example, such as Profinet DCP, can allow to get or set network configuration of these devices. In case of Profinet DCP, in case of Profinet DCP, it also can be very useful for device enumeration. And the last thing about industrial network devices is always remember that these devices with years of uptime can act unpredictably for completely legal and normal activities, such as browsing web page with statistic or login into Telnet. Here my part is over, and now Eugenia will sum up our speech. Thank you.
Thank you, Alex. So the topic of power plants is huge, and the topic of DCS is huge. We just tried to poke a couple of things here and there, and showed that to affect the power generation process, you don't have to go deep to the field level, to PLCs, but you can focus on higher logical levels like application server and automation server. What we do not talk about today is havoc or damage that you can cause by such attacks. Actually, that's because it's not that bad. If you already imagine a hacker in a hoodie who writes a couple of lines and after that the entire city goes into the darkness, it's not like that because it's power grid who is responsible for power distribution. It is not power plant. So here we mostly talk about more local damage, like would it be possible to damage a turbine? Since a turbine is connected to a DCS through PLCs, and the turbine is a giant mechanical monster and it self-degrades by working, probably by putting it into different uncomfortable modes or quickly starting and stopping it. It would be possible to make it degrade even faster or even break it. We were not able to check it, unfortunately, or actually this is fortunately, we were not able to find a spare turbine on eBay. But we are making an educated guess that the damage is out there based on the system architecture. We wanted to make life of power plants a little bit easier, and we prepared a small do-it-your-own assessment guide that you can use to check your SPPA-T3000 system for vulnerabilities that we will discuss today. You just connect your laptop to a couple of places in the network, go through a simple checklist. You don't have to hire expensive security consultants for that. And after that, you can fix some parts yourself, or you can call your system integrators to discuss what to do further. Just any other industrial system, DCSs are not so good in terms of security. It could be better. And we recommend you to take a look at ISA IC 62443 set of standards to know what to do to improve security in terms of communicating with different entities, because in the industrial area, it's usually a challenge when you, for example, when a vendor is not interested to fixing something. So it describes in particular what kind of relationships you can build with regulators, with vendors, and other parties involved in industrial area. Of course, update your systems, change your passwords, improve your configurations according to the vendor security guidelines. We also recommend you to set up monitoring, since most servers are based on standard Windows and Linux boxes. You will not be able to detect different Java attacks, but at least you will be able to detect some parts of attacks. And again, this is more about DCS and industrial security in general, rather than by one system by a single vendor. We released a lot of information. We released a white paper, different tools that we mentioned today. I recommend you to take a look at our GitHub page to find all of that. And we would like to thank Siemens Product Cert, who made all the communications very effective. They were very responsive. They allowed us to contact Siemens product team. And of course, they released the patch. Take a look at the advisory, and Siemens always tries to raise awareness of their users, how to better build such systems, what are better configurations. But they also highlight that it's not the vendor who is solely responsible for security of an industrial environment. There are a lot of things that power plant operators can and must do themselves. So please follow their guidelines for that. That's all for our talk. Thank you very much for your attention, and we will be glad to answer any questions.